Okay, it's about time to get started. So it's my pleasure to introduce today our colloquium speaker, our last colloquium speaker for the semester, Professor Kater Murch, who's here from Washington University in St. Louis. It's great to see someone with such a long Berkeley history done so well and coming back to give a colloquium. Kater did his graduate and postdoctoral work with groups of Dan Stamperkern and Irfan Siddiqui, and he's an expert on quantum systems, on quantum thermodynamics, on quantum sensing, and we'll hear a lot about that today. Also got a slew of awards since his time here at Berkeley, including the NSF Career Award, the Moore Foundation Early Career Award, the Sloan Research Fellowship, and a Cottrell Scholar, so quite a slew of awards. And he's currently the Charles M. Hohenberg Professor of Physics at WashU, and he'll tell us today about new frontiers in open quantum systems, quantum dynamics, quantum trajectories, and quantum sensors. So, welcome, Kater Murch.
Thank you. Can you hear me okay back there? Well, it's a great pleasure to be back here at UC Berkeley after about 10 years, probably since I've been in this lecture hall. And my pleasure to tell you about the research we've been doing in my group at Washington University in St. Louis this afternoon. So before I'm quickly running out of time, I want to take a moment to acknowledge my group and my collaborators and funders that have made this work possible. In particular, today I'll be talking about the work that's in collaboration with these folks here, David Arvidsson Shakur, Nicole Younger-Halpern, Brigida Whaley, Yogesh Yogalkar, and Eli Levinson-Falk. And I want to acknowledge my group. I have an amazing, creative, kind, courageous group of students and postdocs, staff in my group at Washington University, pictured there. And really, everything we've done is due to their hard work. Does anyone know this place? Gavely. So it's a pretty iconic place to go and do physics, and I happened to be there this past fall for a specific focused month talking about new directions in quantum metrology. And part of the benefit of this Kavli Institute for Theoretical Physics is you generate a certain program focused around a certain topic. You bring together world experts, people who are curious about that topic for a month or more. And there's a lot of unstructured time to really just discuss creative ideas. It's part of the beauty of being a theorist. Of course, I'm an experimentalist. Somehow I managed to sneak my way in. And oftentimes those conversations in this room carry on late into the night, maybe on the patio of the Munger residence, where everybody stays at the KITP. And after a few glasses of wine, the ideas get really creative. And it was one such night that I was talking with this colleague, David Arvidsson Shakur, and he mentioned this interesting connection between certain entanglement manipulation schemes and closed time-like curves. That is, these hypothetical trajectories, chronology-violating trajectories of particles allowed by general relativity. And so imagine you were staring out at the night sky. It's a beautiful night, and looking off this way. And whoa, there's a shooting star, but you missed it because you're looking in the wrong direction. Wouldn't it be amazing if you could kind of go back in time and look at the right direction and see what's going on? Of course, you can't do that. But if there's a connection between certain entanglement manipulation routines and closed time-like curves, is it possible to build some sort of time-traveling detector? And it turns out that it is. And I'll tell you about that, but only at the very end of this talk. So give me 40 minutes or so to earn a little bit more of your trust. Build a little more foundation, and I'll tell you the experiments we've done to show that this kind of idea is actually possible. Maybe not in the context of going back in time and seeing a shooting star yourself, but in something a little more physically relevant. Okay. So what's this talk about? This talk is about open quantum systems. This is broadly how I define the research program of my group. So here's a picture of some quantum systems. In this case here, they're qubits or spin-half systems. And open quantum systems are those that are coupled to some sort of environment. And so today's talk will focus on 3 different questions. The first being, does the environment make the energy of these quantum systems complex? As in not a real number, but a complex number. And can that be useful? And what can we see in that case? So this pertains to what we call non-Hermitian dynamics. The second question we'll address is, can the environment have memory? And how do we measure that? And this pertains to what we call non-Markovian dynamics. And then the final topic has to do with what can we measure if we can manipulate entanglement in the right ways. And this will have to do with these time-traveling detectors that I'm advertising. So in addition to all of these 3 topics that I'll talk about today, my group works on a number of different things that I won't have time to talk about in the limited time today. Those include things like quantum thermodynamics. So trying to understand how we can apply the principles of thermodynamics, things like heat and work and entropy and information, to understanding quantum dynamics. How do those extend to the quantum realm? We work on questions of dissipation engineering. How can you design aspects of this dissipative environment to drive quantum systems to specific states that you want or protect certain subspaces? We're also working on new types of qubits, that is, qubits formed from electrons trapped atop the surface of solid neon at cryogenic temperatures. Sounds very exotic, and it kind of is. And we work on quantum materials and materials for quantum information processing, so developing new materials and finding new ways to probe new materials. And we also participate in the quantum detector design for the ADMX collaboration, searching for dark matter. So a lot of things going on. But I'll tell you about these 3 topics that fit together in a nice package today. So let's get started. Does the environment make the energy complex? So here we'll see that there are complex energies that are described by a Riemann manifold. And this gives new ways to control quantum systems owing to the non-trivial topology of those complex energy surfaces. And the way to understand this is by starting with just maybe the simplest way that a quantum system interacts with the simplest environment. That is, here we picture a 2-level system interacting radiatively with the electromagnetic vacuum. Okay? So the dynamics of such an open quantum system can be captured by this so-called GKLS master equation, which is a simple differential equation for the density operator of that qubit, and it has different components to it. So one has to do with the unitary evolution of the qubit. That is some sort of kind of Hamiltonian coupling we have that's driving on the system. There's something called a jump term, and then a coherent non-unitary term. So a simple equation with 3 terms. And one of the cool things about this equation is you can see, or you can trust me, that if you're able to eliminate this middle term, the so-called jump term, from those dynamics, you can recast these other terms here into a new effective Hamiltonian that's a generator of time translation. And so the remaining effect of the dissipative coupling to the environment is that this new Hamiltonian is expressly non-Hermitian. You can see that here. Okay? So this is a simple way to generate non-Hermitian dynamics, which will lead to some interesting things, as I'll show you in the coming slides. Okay? So all we have to do is eliminate the jump evolution. So how might we do that experimentally? You can imagine surrounding this atom with a bunch of photon detectors, and then just making sure that none of those photon detectors click. Okay, and that way we would have the dissipative coupling to the environment, but without quantum jumps. Now that's a little impractical. We actually found a simpler way to do that in practice. Okay, so the experiments I'll tell you about today have to do with superconducting qubits. And I know there's a few prominent groups here at this university that do this. In fact, this is how I learned all these techniques. But I'll mention briefly, for those who are not familiar with that work, that these circuits are made from superconducting elements such as a Josephson junction, a capacitor, And a superconducting transmon qubit takes place in a regime where the Josephson energy is greater than the charging energy associated with the capacitor, which case you can think about the qubit as simply the bound states of a certain potential as a function of this flux associated with the Josephson junction. Forms a cosinusoidal potential. And so we'll use the lowest 3 or 4 bound states of this potential as our quantum system for all the studies that we'll do today. In practice, this is a device fabricated from aluminum deposited on silicon. This is actually a picture taken back from my time here at Berkeley. So it's aluminum oxide, aluminum on silicon. And we can embed these circuits inside a 3-dimensional cavity to realize the physics of cavity quantum electrodynamics. Great. So here's how we isolate the no-jump evolution for this open quantum system. We're actually going to use the 3 lowest energy levels of this transmon circuit. So we'll label them G, E, and F. We'll arrange things so that there's a strong dissipative coupling of this excited state to the ground state. But now I'm going to redefine my qubit to just involve those 2 higher energy levels, the ones E and F, and I might initialize the system initially up in this F state. Okay? So then we'll let the system evolve with the presence of this dissipation from the excited state over time. And as you can see by the diagram, that evolution involves some coupling between these 2 states at rate j. So we're going to drive the system while it's decaying. And then after some period of time, we'll make a measurement of this circuit in its energy basis. That is, we'll make a projective measurement on these 3 states. So we might find that the qubit is in its excited state. We might find that the qubit's in its F state. But if we found that it's decayed to the ground state, then a quantum jump has occurred. We want to eliminate that from the dynamics, so we throw away those experimental results. So we're just looking at the case of this dissipative qubit where it does not undergo such a quantum jump. Okay, so if we do all that, we have an effective non-Hermitian Hamiltonian. Now let me give you just a little intuition about what this does. So for comparison, consider a Hermitian qubit. So here I've set the decay rate gamma equal to 0. In this case, I'm simply driving Rabi oscillations from the excited state, from the F state to the excited state and back, and so we see simple cosinusoidal probability of the qubit remaining in the F state. So for comparison, if I turn on the dissipation to create this non-Hermitian Hamiltonian, you see the Rabi oscillations are highly distorted. That is, it slowly decays down from the F state to the E state, and then rapidly returns to the F state. So this is the combined effect of the drive and the role of this non-Hermitian Hamiltonian. One can see this as the measurement back action from the post-selection pushing the system to the F state. That is, since the excited state has a high probability of decaying, we're throwing away all the results where it decayed. The fact that it hasn't decayed means it's more likely to be in the F state. And so it's the combination of that sort of measurement back action and the drive that leads to this effect. Okay. So this is a simple 2-state system, so we can write down the Hamiltonian, which is just a 2-by-2 matrix. The relevant parameters are J, which is a coupling rate between the excited state and F state, just proportional to the amplitude of a microwave drive, and delta the detuning between those 2 states. Okay, the 2-by-2 Hamiltonians here, and you can see it's obviously non-Hermitian because they've got an I on the diagonal. So what do you do in a quantum mechanics class when you're given a Hamiltonian in matrix form? Well, the first thing you do is diagonalize it to determine the eigenvalues of this Hamiltonian. So I asked Mathematica to do that for me, and I get these nasty expressions for the eigenvalues, the 2 eigenvalues of the system. They're complex. That is, the Hamiltonian is not Hermitian, and we usually use the assumption of a Hermitian Hamiltonian to guarantee that we'll have real energy eigenvalues. But that's no longer the case. Okay, so since they're complex, let me plot for you the real part and the imaginary part of the energy eigenvalues of this simple 2-by-2 Hamiltonian. So here's the real part, here's the imaginary part. The 2 parameters we care about are the detuning and the coupling rate J, and they form these beautiful Riemann surfaces that describe the complex energy landscape of this system. I'll bring attention to a degeneracy in the system, the so-called exceptional point degeneracy. This is a place where both the real part and the imaginary part of the energy are degenerate. And the special about these exceptional point degeneracies is that it's not only the energy eigenvalues that are degenerate, but the eigenvectors themselves are degenerate. That is, the Hamiltonian is no longer diagonalizable at this exceptional point. This has interesting consequences for the dynamics around such exceptional points. Great. So this is an example of what we call a PT dimer, where PT stands for parity time, or parity time symmetry. So here a system you can think of as the E state decays away, F state and they're coupled. And so you can kind of transform this to a case in an overall decaying frame, where the F state has gain relative to the excited state, which has loss. This has parity time symmetry because if I apply the parity operator that exchanges E and F modes, and time reversal turns this gain into loss and loss into gain, restoring the same system. And these kind of PT dimers appear in all sorts of systems because they just involve two modes of coupling where we have imbalanced amount of loss. So for example, Jack Harris's group at Yale studies such systems in the context of optomechanics, where he uses cavity amplification and cavity cooling to create damping and amplification on certain modes. There are instances of studying such things in trapped atoms. You can imagine two spin states, where one of those spin states is coupled to the continuum. And so now you have these two modes, the two spin states, that have imbalanced loss. Or you can study such thing in microtoroidal ring resonators, as pictured here, where you can use doping of these ring resonators to create gain or loss. In our group, we're extending this into a much more quantum domain, where those sources of gain and loss can correspond to quantum squeezing and amplification of the electromagnetic vacuum, a case where there's actually no dissipation or dissipation-free non-Hermitian dynamics. Okay. So one of the most striking features of this exceptional point, the degeneracy of this non-Hermitian Hamiltonian, is the physics of dynamical encircling around that degeneracy. So to remember, the two parameters you can tune are delta, the detuning, and J, the coupling rate. So imagine initializing the system in an eigenstate of the Hamiltonian for some choice of those parameters, and then slowly tuning the parameters so as to encircle the exceptional point. What would happen? Well, to gain some intuition, we can plot the real part of the Riemann, the real part of the energy eigenvalues shown here, and imagine starting with this initial state and then slowly tuning those parameters. We imagine the state to adiabatically follow the instantaneous energy eigenstates, so it will continue along, passing through this branch cut, continuing to the lower Riemann manifold. That is, the initial and final parameters are the same. We've made a closed loop, but we started in one eigenstate and now we're in the other eigenstate. So it's fundamentally different than encircling a normal Hermitian degeneracy. So let me show you a little experimental data where we actually demonstrate this effect. So what we're going to do is we're going to take that evolution, we'll divide it into successively longer chunks of time, pausing at each end of those experiments and measuring the projection of the spin along its different polyaxes to determine the polyexpectation values as a function of time and therefore sweep around the loop parameters. So the results are here. So the solid lines are experimental data, and the dashed lines are just a calculation of the instantaneous energy eigenstates of the Hamiltonian. And so you can see the system starts off in one eigenstate where the expectation value of sigma x is -1, and it passes to where the expectation value of sigma x is +1. And if we encircle it around the exceptional point in the opposite direction, well, the same thing happens, except it passes in one case through the excited state and in one case through the ground state. There's a lot of things we had to do to make this experiment work. We had to use counter-diabatic controls to be able to make the loop parameters sweep fast enough and to remain in the adiabatic regime. There's all very interesting connections to geometric phases that are current with encircling such degeneracies, and so forth. But this becomes really interesting if you can extend this kind of encircling behavior to higher dimensional exceptional points. That is, consider a case of a threefold degeneracy, EP3. One can imagine a surface of EP2, that is twofold degeneracies, that connects to this EP3 region. And it turns out in this case, in the control parameter space, a constant distance from this threefold degeneracy, one can consider encircling the exceptional point once, twice, or 0 times. And these correspond to different control parameters that would exchange the energy eigenvalues of the Hamiltonian either 0 times, or a pair of them, or braid all 3 energy eigenvalues. So you can see that the topology of the manifolds describe these complex energy landscapes that become very rich when you consider higher energy exceptional points. I won't dwell on this too much. I lost the slide, apologize. I won't dwell on this too much because I don't yet have experimental results to show you in this context, but I'll tell you that it's very exciting and very confusing. One more project to mention in the context of these non-Hermitian dynamics is that of speeding up entanglement. So this is something we worked on in collaboration with Brigitte Whaley's group, where her postdoc Zhengjiao Li and my postdoc Weijin Chen devised a method to speed up entanglement between qubits in a way that you can't achieve with strictly Hermitian qubits. So for comparison, if we have two normal Hermitian qubits and they interact with some rate g, you'd expect the time scale for those two to become entangled to scale inversely proportional to g. But it turns out if we have these PT dimers operating near the exceptional point, so we have the same driven system that has dissipation out of the qubit manifold, you can have entanglement generated between these systems much, much faster than the inverse coupling rate between the two qubits. And the intuition behind that comes from those same distorted Rabi oscillations that I showed you many slides back. That there are moments where the effect of the measurement back action, the non-Hermitian dynamics, and the drive, or the coupling between the two, coincide to accelerate certain dynamics, certain accumulation of phase, so you can end up with highly entangled states over time scales that are much, much faster than the coupling rate. Very fascinating effects. Okay. So let's take a quick pause for a question or two. Give me a chance to catch my breath. But let me summarize what I've told you so far. The idea is that by post-selecting on this no-jump evolution, we can generate an effective non-Hermitian Hamiltonian. This non-Hermitian Hamiltonian has complex eigenenergies, and we can tune the parameters so as to encircle the degeneracies of these eigenenergies. And what's cool is that the eigenenergies are now complex, so they have interesting topology. And this topology reflects in the way that we can control the quantum state as we transport it adiabatically through this complex energy state space. A question, just to shake us out of our things. Dima is hoping you can ask one. Yeah. So it depends on the way that they decay. So if we have a situation where the one state decays to this one and this one decays out, it's actually the contrast in the two decay rates that leads to this non-Hermitian effect. So if the decay rates are equal, then it's described by just a dissipative interaction, but there's no non-Hermitian part to the Hamiltonian. So we need this actually, the difference in decay rates that leads to these interesting physics. One context that this is actually showing up more and more in the literature is in the context of what people call dual rail encoding for quantum computing, where one is able to effectively erase decay events by asking, do you need both decay events to sort of happen in tandem? In this case, you can have, it works really well if you have exactly the same decay rate for the two systems, because those cancel out. But if you have different decay rates, then you end up with an effective non-Hermitian Hamiltonian. We'll save your question for the end. How about that? Okay, let's move on. Non-Markovian dynamics. The question is, does the environment have memory? And that would be interesting, because if it did, then we have to keep track of what had happened in the environment for all of its history. It would be quite complicated to keep track of. So this GKLS master equation, pictured here, which we use to describe just a simple atom decay with an electromagnetic field, but could describe much more complicated situations. Say it might have many different dissipative channels that we have to sum over, hinges on something called the Born-Markov approximation. That is, that the environment has no memory, the Markov approximation. It's a great equation, but what if that's not the case? Then this equation no longer applies. In fact, it might be quite interesting, and there might be applications associated with non-Markovian environments, memory effects in the environment. Those might have to do with things in quantum communication, quantum control, coherence preservation, and so on. So how do we measure non-Markovianity? Well, let me back up a bit and just talk about using qubits as sensors in general. Qubits can make very good probes of the environment. On one hand, here's a T2 time measurement, a Ramsey measurement of a qubit, decays in 1 microsecond. That's pretty short in my language. But if you turn that around and say, well, this is a very good probe of what's going on in the environment. The T2 time is a measurement of the fluctuations at low frequencies. So we can actually use the decay of coherence of this thing as a probe of the environment. So in fact, Ramsey measurements, Rabi measurements, energy decay measurements are all probes of the spectral density of fluctuations in the environment at different frequencies. The lowest frequencies are for Ramsey measurements, the highest frequencies for T1 measurements. And this goes by the name of noise spectroscopy, that you can use the decay of these quantum systems as a probe of the environment. In fact, Shimon, sitting right here, has a seminal work where he was able to use this type of T1 spectroscopy of nitrogen vacancy centers in diamond as a probe of the Johnson noise of metals right near the surface. We're employing the same techniques in my group in collaboration with Chong Zhu and Shankar Mukherjee and Eric Henderson for optically trapped nanodiamonds in aqueous environments. Again, using this T1 spectroscopy to measure the nanomolar impurities of paramagnetic spins. Okay, so this very ubiquitous technique. But in the hierarchy of different types of quantum sensors, detailed in the seminal review from Deegan, Reinhardt, and Capillaro, there are three categories of quantum sensors. And the T1 spectroscopy technique might be considered to be the simplest kind of quantum sensor. That is, a type 1 quantum sensor that hinges on the existence of quantized energy levels, but not necessarily individual control over those atomic levels. So this is what you see in NMR and MRI imaging techniques. More sophisticated quantum sensing technologies utilize quantum coherence. So for example, things like atomic fountain clocks, atom interferometry, color center magnetometry, superconducting quantum interference devices. But the most powerful kinds of quantum sensors utilize entanglement. So what they call type 3 quantum sensors. Here we see things like Heisenberg scaling or GHZ states, spin squeezing. So this is the technology employed by advanced LIGO to squeeze the quantum noise in an interferometer to look even deeper into space for black hole mergers. So those are certainly the best types of quantum sensors, the kind that really give you truly the most powerful non-classical advantages. And so this question of type 3 quantum probes in the context of open quantum systems led us to search for ways to measure properties of the environment in a way that harnesses entanglement. So I've told you about qubits as a probe of the environment, that is qubit noise spectroscopy. But what if you had entangled qubits as a way to probe aspects of the environment? Could we measure correlations between different parts of the environment in a way that you couldn't measure otherwise? Could we measure memory effects in the environment? And that's in fact what we can do. I'll show you that now. Okay, so in the context of characterizing non-Markovian dynamics in open quantum systems, there have been two primary methods put forward in the literature a decade and a half ago. The first is the so-called trace distance method that involves initializing two different states, rho 1 and rho 2. And the idea is a typical GKSL master equation evolution will only cause the distance of those two states to get closer and closer over time. So if one sees a situation where the distance between these two states is growing, it's a signature of non-Markovian dynamics. However, there's another method proposed by Rivas et al. In 2010, which has to do with an entangled probe. The idea of an entanglement revival. The idea is we have a probe in an ancilla, or a system in an ancilla, the two are in some maximally entangled state. One of those interacts with the environment. And the idea is if I ever see the entanglement between these two increasing over time, that's a measure of the non-Markovianity or quantum memory effects in the environment. Okay, so here's the schematic of such an experiment. We're going to use two qubits, one as we'll label qubit, one ancilla. We'll prepare those two in a maximally entangled state. We can then let the qubit interact with the environment. And the interaction is going to cause the qubit to become entangled with the environment. But due to this concept of monogamy of entanglement, that means that the entanglement between the qubit and ancilla has to go down. Okay? But if the environment has quantum memory effects, it's possible for that entanglement to flow back into the qubit ancilla system, restoring the entanglement between the qubit and ancilla, forming a smoking gun signature of non-Markovian or quantum memory effects in the environment. Okay, so to perform such an experiment, we designed this now experimental platform involving 3 qubits. Okay? The qubits now are these cross-shaped pieces of metal, and they have all sorts of control circuitry and so forth and so on. We can form entangled states between the qubit and ancilla by parametrically modulating the frequency of the qubit to bring it into resonance with the ancilla qubit. If we do that for just the right amount of time, the two end up in a maximally entangled state. And we can generate those entangled states with a fidelity of roughly 95% and a concurrence, which is a measure of whether the two are entangled, of 0.95, where 1 is the maximal entanglement between the two. Okay, so let's focus on just the qubit and ancilla part of this process there. We've prepared them in a maximally entangled state, but then we'll turn off the coupling between the qubit and ancilla. And if we just wait for longer durations of time and measure if the two are remaining in an entangled state, what we see is the following change in the concurrence. It decays slowly over time from roughly 0.95 down to some lower value with an exponential time scale that's simply consistent with the T2 times of the individual qubits in ancilla, which is roughly 40 microseconds apiece. Okay, so that's not very interesting. It's expected from their normal decoherence rates. Now we'll introduce coupling between the qubit and the environment by modulating, again, the environment frequencies to bring it into resonance with the qubit. In this case, I see the concurrence, or the entanglement between the qubit and ancilla rapidly decrease, but then revive and then decrease and revive and decrease and revive. So this is a smoking gun signature of quantum memory effects in the environment because the entanglement is decreasing and increasing and decreasing and increasing. And that's not very surprising because the environment itself, as you can see, is just another qubit. Of course it has quantum memory effects. But we can tune the quantum memory effects of this environment by adding additional photons into the environment, a Markovian bath for this non-Markovian environment, if you will. So what I'm going to do is I'm going to add dephasing to the environment at a rate of gamma. So if I add a small amount of dephasing to the environment, what I see is these are revivals of concurrence are smaller each time. And that makes sense. There's some sort of loss of information as the environment carries the quantum information from the qubit and returns it to the qubit. But if I increase that dephasing just a little bit more, I see now the entanglement abruptly decreases and stays monotonically decreasing. We now see no more any quantum memory effects. Okay, so for fun, let's just continue to increase the dephasing. Now I add even more damping to the environment. And you can see that now the concurrence decreases slower than it did before. More damping means slower decay. Increasing it even more, I get to a place where now the decrease in entanglement is vanishingly slow compared to the case where there's no coupling to the environment. So let's analyze this transition from what we call Markovian or non-Markovian behavior to Markovian behavior more quantitatively. Okay, so the first thing is to look at this non-Markovian measure introduced in this paper back in 2010. This equation roughly just integrates over all the points where the concurrence increases. Those are signatures of memory, quantum memory flowing back into the qubit and ancilla probe system. Okay, and so we can calculate this measure, and you see it's a value of roughly 1.4 for very vanishingly small damping on the environment. But as we increase the damping on the environment, going horizontally here, we see that this measure goes down to 0 and stays flat roughly. The other way to look at this data is to look at the decay envelope of the concurrence. That is, we can fit these recurrence revivals to an exponential, and we can determine an overall decay rate for the concurrence, capital gamma C. So as I increase the dephasing on the environment, we can see this decay rate gets faster and faster and faster and faster, but then it gets slower and slower and slower and slower. So here we see a case where as we increase the damping, we see a very abrupt change in the decay properties of the entanglement between the qubit and ancilla. Okay, so this entanglement probe of quantum memory, we're able to observe these quantum memory effects of the environment, but actually most intriguingly is this entanglement probe is the only true probe of quantum memory effects in the environment. One can imagine cooking up some sort of classical environment that involves, say, measurement and feedback on an environment that would give you a trace distance that increases over time, but it would simply be a classical environment that has external controls. So in the context of probing sort of quantum features of decoherence, these entangled probes can be valuable in determining the quantum nature of an environment. The other facet that's quite interesting here is a part of dissipation engineering. We see this interesting case that as we increase the dissipation, we're getting increasing coherence. Normally we think opposite is the case. Increasing dissipation means decreasing decoherence, decreasing coherence. And that certainly happens in this regime here. But here we're into a regime characterized by the quantum Zeno effect, that enhanced dissipation, enhanced measurement pins the state of the environment, preventing it from causing decoherence on the qubit and ancilla substates. Okay. That takes us to the end of question 2. Does the environment have memory effects? So we used an entangled probe to measure quantum memory effects in the environment. We added dissipation to this environment to create a transition from this non-Markovian behavior to Markovian dynamics that can be well described by this GKLS master equation. And we ultimately found this regime where the dissipation stabilizes the entanglement between the qubit and ancilla, which is an example of how dissipation can be a resource for preserving coherence. I'd be happy to take a question if someone wants to break the ice for a moment. Yes?
Usually a path is much bigger than the system. So if you have a much bigger path size in the system, do you just like the environment or
Yeah, so the question is, usually the bath is very large compared to your system. And in that case, would you lose this effect as the environment having memory? And so generally, when the Markovian approximation is very good because the environment is big and it does have large number of degrees of freedom. So the revival time for information to flow back into the probe could be very long. You would never see such effects. In which case, for all intents and purposes, a Markovian description is fine. But there's certain circumstances, say in a modern quantum processor with 50 or 100 quantum bits, where these non-Markovian effects can be quite problematic. That is, you have qubit A and qubit Z happen to have similar frequencies. And so there's coupling between the two, and there's quantum memory effects that are difficult to model, keep track of with a simple master equation approach. So what's powerful about this is now I can use this Zeno effect to pin the state of the environment, to let this quantum processor work by making the environment not only Markovian, but now decoupled from the system. Yes? Is there a time reversal symmetry breaking in the system? I would say that in the case of a Markovian environment, the time reversal symmetry is broken. That is, we have just an arrow of time in the dissipation flow. And so I think, but that's my main comment on that. Okay. Let's come back to where we were at the beginning of the talk. That is it possible to harness entanglement to build a time-traveling detector? Now, I know that sounds crazy, or crazy awesome. But it's maybe not so crazy, or maybe it's not so irrelevant in this current era of multi-messenger astronomy. That is, we currently have the capability that we have many detectors. I lost my slide. Oh well, we'll come back there. We have many different detectors pointed to the sky in different ways. And one may get a gravitational wave signal that tells us that we'd like to have optical detectors pointed in a certain direction. And would there be ways to have those optical detectors oriented in a certain direction after the fact using entanglement? Okay, so the first thing I want to say is that entanglement is, of course, the key to quantum technologies. It's the power behind quantum computation, quantum communication, quantum simulation. And the few things that I've learned about entanglement over the years. One of those is that entanglement is complicated. That is, this pertains to the exponentially large Hilbert space we get as we have a larger number of quantum systems that are entangled. That's in some sense power of quantum computation and the power of quantum simulation. But the other thing is that quantum mechanics is spooky. And I'm talking about spooky action at a distance. So think about the typical Bell's inequalities experiment, where one maybe starts with a spin singlet state here, a total spin 0 along any direction. Now we know if we take these two spins and we separate by some distance, if I make measurements on the two different spins, the results are always anti-correlated. So I can measure them in the z basis, and one would be spin up and one would be spin down. And I can measure in some other funny basis, and one would be spin sideways, another one would be spin sideways. And of course, this is what's captured by Bell's inequalities. And in fact, it was fascination with Bell's inequalities, the development of his inequalities, and tests of these inequalities, a lot of which happened here at UC Berkeley, that's really responsible for where we are now in the so-called second quantum revolution. That is, the technology we had to develop in order to do those things, the persistent interest in quantum entanglement is what we're trying to harness now in terms of building quantum sensors and quantum computers. But here's one thing that I learned that's rather interesting about entanglement, and this was again at this KITP workshop, is that there's a mathematical equivalence between closed time-like curves, that is, things pertaining to time travel, and entanglement manipulation. And in some sense, this helps demystify Bell's inequalities. So the way to see this is to let the symbol U, it's actually a cup in LaTeX, represent the preparation of this maximally entangled state, the spin singlet. Okay? So then a closed time-like curve can be expressed in the following ways. I prepare at some initial time, so time's running vertically, a spin singlet state, and then sometime later I measure in an entangling basis in the spin singlet state. And so long as I prepare and measure the same state, I can think of this as a single trajectory of a particle stuck in a closed time-like curve, going forward in time and backward in time. Okay? So in the context of this measurement correlations in Bell's inequalities, I can imagine here's preparation of my spin singlet state. The fact that one spin is up and the other spin is down, even though they're very separated by one another, can be seen as the fact that they're the same particle. One of them is simply going backwards in time, turned around by the entangling measure, which also happens to flip its sign, and then it's seen on the other detector. Okay, so if you found spooky action at a distance spooky, you don't have to worry about that anymore. You just say it's time-traveling particles. Just which one do you think is more quirky? Okay, the other place that this kind of gives some intuition is in the familiar teleportation algorithm. So as you might know, teleportation of a quantum state takes place in the following thing. I have my quantum state I want to teleport, and I make I'm a maximally entangled state. I make a joint measurement of my state with one of those half of the entangled state. And then 1/4 of the time, my state is teleported over to the other half of that entangled state. Other 3 times, all I have to do is use the outcomes of this measurement to make some local operation on this to fix the state. Okay? But of course, via the language of closed time-like curves, I can think of this as simply one particle's trajectory. It goes forwards in time, turned around by this entangling measurement, goes backwards in time, turned around by the entanglement generation, and goes forward in time. Okay, you guys are thinking this is ridiculous, but this is the sort of stuff that takes place at KITP. If you don't like it, you don't have to go there. Okay, yeah, so here's the idea. Can we harness this idea in the current era of multi-messenger astronomy? Might be relevant, but will be kind of challenging, but I actually don't think it's so crazy. Okay, so this idea inspired an experiment that we performed just this last fall and this spring to demonstrate this idea, but not with telescopes and not with optical detectors, but of course with qubits, because we're a qubit lab and this is talk about qubits. And the idea is that these closed time-like curves inspire optimal metrology with qubits. And the context of this, this experiment has to do with sensing a rotation. So the protocol is drawn here, time's running vertically here for the rest of the talk. And I have some initial state I need to prepare. and the state of my qubit undergoes some rotation, some angle alpha about some axis n hat that I don't yet necessarily know. And the thing you might understand about sensing rotations, which is really the most platonic form of measurement you can imagine, that is the most idealized, simplest case, is that we have to choose the state of the spin appropriately for the axis of rotation. That is, if the rotation is along the z-axis, and I orient the spin in the z direction, the rotation has no effect. So the sensor was prepared in non-optimal state. The rotation of the z-axis, I need to prepare the spin, say, in an equal weight superposition of those eigenstates so that it acquires some phase. Okay, that's pictured here. So if this axis is z hat, I started with a state that's pointed in z, then the quantum Fisher information is 0. Quantum Fisher information is a measure of how much classical information, or it's a limit on how much classical information I can get about the rotation angle from the evolution of the quantum state. As people who are experts in Ramsey measurements in the audience know, you need to, in order to measure a z rotation, we need to prepare the qubit along the equator of the Bloch sphere. That is an equal weight superposition of the maximum and minimum eigenstates of the generator of the rotations. More generally, an arbitrary rotation is specified by 3 angles. It's the rotation angle alpha, azimuthal angle phi, and the polar angle theta. 3 parameters you need to know, but a qubit only has 2 degrees of freedom. So in general, you can't measure 3 unknown parameters with 2 degrees of freedom. Sensing an unknown rotation with a single spin half is an impossible task. Okay, and the quantum information, Fisher information is important because it goes into something called the Kramer-Rao bound. This is a bound on the variance of our estimator of the parameter alpha, which is limited by the amount of data that we have in the quantum Fisher information, which bounds the classical Fisher information we have about those things. And in this case, the maximum quantum Fisher information about a rotation angle alpha is 1. Okay, so that just illustrates the problem of trying to measure an unknown rotation with a single spin. But can we use this time travel trick to measure the rotation angle if, for some reason, at some later time, the axis of rotation is known? That is, at time t1, when we start everything in experiment, the rotation axis is completely unknown. What we'll do is we're going to prepare our maximally entangled state. That's this U state, or this cup shape right here. One half of that entangled state, we'll call it the probe, experiences this rotation. We still don't know what the axis of the rotation is. But after the rotation's happened, we find out, turns out in this case, the rotation axis was along x. Now that I know which way the rotation, which axis the rotation was applied about, I can choose the measurement basis on my ancilla to prepare that qubit, to project that qubit into a state that would have been optimal for measuring this rotation. That is a z state. Okay, but via the sort of language of closed line that curves, what that does is it sends this state backwards in time, turns around to be exactly the optimal state for being sensed by that rotation when it occurred in the past. Okay, so this is what we call hindsight metrology. And does it work? Of course it works. So here's a measurement of the Fisher information that we obtain about the rotation angle alpha as a function of the rotation axis theta. So for each rotation axis, we only find out the axis rotation after it's occurred. We can make measurements that depend on that axis of the ancilla to prepare the qubit in the optimal state for making measurements of this rotation. And you see we get a quantum Fisher information that's flat across the whole thing. It's not 1, as would be the best case. And it's not 1 because, well, you can only prepare this entangled state with a finite fidelity. But it's much better than 0. And it's much better than 2/3. Turns out that 2/3 is the best you can do with 2 qubits with no entanglement. So you have a real quantum advantage due to entanglement. Okay, it compares 0.8 to 2/3. It's a small advantage, but it's real. Okay, but you're saying this is kind of contrived, Kater. When is it that you don't know what the rotation angle is going to be, but then you learn afterwards? Well, actually, this is the sort of thing that's going to happen with multi-messenger astronomy, but that's decades down the road. But what if you never know the axis of rotation? Can we use this trick in that case? And of course we can. So this is something we call agnostic metrology. That is, we want to measure some rotation alpha, but we never get to know what the rotation axis is. And so in order to measure that with the maximum quantum Fisher information available, what we can do is we can embed this rotation in a true closed-time-like curve, or a simulated closed-time-like curve, because those don't actually exist. To prepare an entangled state, we project in an entangled state. In this case, if these two entangling preparation and measurement, that creates a closed-time-like curve. The coupling to the sudden rotation is like the interaction with the field that knocks this particle off of its closed-time-like curve. So the success probability of simulating this closed-time-like curve gives us information about what the magnitude of this rotation is. And in fact, it gives us information that attains the maximum quantum Fisher information about that parameter available. Okay, so that's pretty cool. We're currently working on generalizations to larger spin states. So what happens if we go beyond b equals 2? The q-trits and q-dits or larger spin systems, how does this advantage scale? Does it scale? Turns out that there's real advantages available in the sensing of depolarizing channels with this approach. So go back to the T1 spectroscopy, but now redo that in the context of entangling that spin you're sensing with some sort of ancilla. One can garner more information about the depolarizing channel using this strategy. We're just figuring that out. Turns out that this is hard, though. Of course, using these quantum technologies requires entangling things and measuring entangled bases, and those are hard technologies. They're classical challenges we have to overcome, and very quickly, the infidelity of creating entangled states starts to mire any advantage that we have from the entanglement. So it will finally be interesting to kind of generalize this to optical cases. So what if instead of the spin state being the thing that we're entangling, it's the optical mode? In that case, you might really have a sense to choose which way a photon detector is pointing in hindsight. Okay. Maybe as a final few minutes of closure here, let's return to the overall theme of the talk, which is about open quantum systems. Now, we can all agree we want to know how to make quantum technologies work. And I mean like really work, how to make quantum computers that actually deliver real-world advantages, quantum sensors that really outperform anything you do with classical cases, quantum communication that securely transmits information from one place to another. These things that really truly harness the power of quantum technologies have been promised, for as long as my career has been around. And in doing so, we're tending to focusing on the problems of decoherence and dissipation. Oh no, my G time is only 1 microsecond. Oh no, my qubit, which is initialized in a thermal state, in a pure state, is ending up in a thermal state over some short period of time. But I'd argue we should really be asking, how can we use the interaction with the environment not as a problem, but as a solution? That is, how can we harness dissipation and decoherence to be helpful? You can sort of think about, there's many cases where that's the case. So laser cooling, we're using dissipation to get our atoms cold and do all sorts of cool physics. So let's extend that concept a bit. And there's sort of 3 facets to this talk or to my research that are tackling this question. So one of those has to do with the fact that thermodynamics and statistical mechanics have been profoundly impactful in many areas of science, not just in the development of steam engines, although they saved probably hundreds of years of effort trying to engineer more efficient steam engines, just knowing that you can't get beyond a certain bound. Wouldn't it be great if you had the same sort of guidance into generating large-scale quantum computers? On the other hand, dissipation, of course, provides powerful ways to control, to initialize quantum systems, to protect them from decoherence, to engineer quantum subspaces. And then the final facet is that sensors and sensing and using systems as measuring pertains deeply to concepts of information and entropy, things that are closely intertwined with thermodynamics. So I'd argue that by marrying these 3 topics and working in the cracks between them, we can really make a step forward in getting quantum technologies to work. So maybe the overall statement would be, if we want to make technologies work, we have to find ways to understand and harness the effects of the environment. And I hope my talk has given a couple facets of exactly how we can do that and some of the fascinating things in that story. Okay, so that's the end of the talk. To summarize this last little bit, there's a mathematical equivalence between closed-time-like curves and entanglement manipulation, and we can harness that in certain ways to inspire new types of ways to use entangled states to measure things in ways we might not have considered otherwise. Okay? So something that goes from a crazy creative discussion over a glass of wine to maybe some impactful methodological approaches in the near future. If you want to know more about that, there's a paper on the archive about that, and there's lots of references about closed time-like curves and all these things in this wonderful paper, so you can go ahead and read that. But otherwise, I'll thank you for your attention and take questions. Dima. Oh, yes. So the question is, you talked about this in the context of rotation sensing, but you never mentioned what the experimental platform is. Indeed, I could have done that. Our experiments, of course, is the same exact system that we use for this non-Markovian in dynamics, the same entangled probe or qubit in oscilla system. And so in this case, the rotation, well, it's actually a physical rotation on one of these qubits generated by a microwave drive and phase evolution. Okay, so it's a synthetic experiment in that we generated a known rotation to the qubit, and then we measured exactly how sensitive the qubit was to that known rotation. The qubit is, again, a superconducting transmon qubit. So in that case, it's a demonstration experiment rather than measuring like a true magnetic field. But it might not be all that hard to do this with NB centers if we can make all the right, entangled states and measure the states with reasonably high fidelity. Yes.
Maybe you said this and I missed it. What is the difference between your closed timeline curves and your agnostic phase information and teleportation?
So teleportation. Okay.
Teleportation protocol.
Okay. The teleportation protocol involves 3 qubits. So we entangle 2, and we measure 2 in entangled bases. This agnostic sensing thing only uses 2 qubits. We entangle them and we measure them. So in some sense, it's the 2-qubit version of that. The entanglement the 3-qubit protocol has actually a bunch of very interesting extensions to it. So one can then use this for weak value amplification or other things like this, where 1 qubit is getting some weak signal from some other field. So there are definitely 3-qubit extensions, but in this case, that's the main thing. It's 2 qubits versus 2.
And in your first bit, there was some information that was propagated, like classical, like, hey, I measured along X. So that
Yeah.
has to be transferred.
So in a normal entanglement protocol, I have my state and my entangled pair, and I measure 1/2 of my entangled pair with my state I want to teleport, and I'm measuring in a Bell basis. There's 4 possible outcomes. One of those outcomes corresponds to the singlet that I prepared here, in which case this is the perfect case that corresponds to this trajectory of the particle going forward in time, backward in time, forward in time, ending up teleported over there. But that only happens 1/4 of the time. But it turns out that I can take the other 3 cases, and then I know exactly what local operation I have to do on this other qubit here to get it to be the initial state there. And that's this local, classical communication and local operation that people use in teleportation algorithms. In our case, in fact, we have this preparation of the spin singlet state. We're measuring the spin singlet state in our agnostic sensing thing. But of course, we're just looking at the probability that's still in a singlet state. But there's actually other measurement outcomes that can take place there. There's 4 possible measurement outcomes. And those actually carry more information about the direction of the field. So we can get almost vector information about the field from the fact that we have 2 bits of information coming out of this measurement. But measuring in a generalized complete Bell basis is actually quite hard for us to do in implementation, so we just measure singlet or non-singlet. But there's more to be squeezed from this. We have better measurement. Bill?
Yeah, you talked about applications to multi-messenger astronomy. You want to give us your most exciting prospect?
Oh, okay. I mean, this is very speculative.
This hanging there.
So, this is down the road. But one of the most exciting things in my mind for astronomy going forward is this idea of entanglement-assisted telescope arrays. So the idea is that you have, telescopes, separated by large distance, long baseline optical interferometry. It's very challenging to get the photons from one telescope to the other, especially if they're separated by thousands of kilometers. But their proposal is to use this teleportation trick to effectively take the photons from one telescope and teleport them to another telescope so we can do long baseline interferometry. It's a very challenging, speculative thing, but those technologies are emerging. In fact, Alp Sitahogil at universities, one of the people working toward this thing. Okay, That's a case where you're already taking these incoming photons, and you're entangling, writing those into quantum memories, manipulating, moving with entanglement. And so in that case, I do think it is reasonable to think like, if we want to take this optical mode and this optical mode and use those to swap them and to interfere that would be relevant, and to make those choices after the fact would certainly be possible, because now we're really playing the role in the case of quantum entanglement. So it'll take a bit of collaboration and a bit of work with people who are real experts in these things to write papers that demonstrate that we can point to telescope after the fact, but I don't think it's impossible yet. So that's my goal. Yes?
When talking about quantum computing and entanglement, we often make the assumption that the laws of physics are linear with respect to superposition. That is to say that Schrodinger's dead cat and a live cat don't communicate. But what if, like many things in the universe, actually that's nonlinear?
Yeah, could be quite interesting. And I don't know what would happen in that case. I'm already plenty confused working in the paradigm of linear quantum mechanics. So, but we could certainly discuss that. Yeah, we'll get you eventually. Go ahead.
So, yeah, I think the prospects of experiments on open quantum systems are really fascinating. Can you comment on like how we can learn from this, for example, repeating experiment towards, for example, theory that something that you cannot directly compute from theory?
Yeah, so the question is, what can we learn from these small experiments to something we can't directly compute from theory? I would love to have a really solid answer to that, because that's certainly the place we want to go. One of the things that's most bothersome about being an experimentalist working with only a few qubits is it's pretty easy to model exactly what's going to happen. And at some point, you're like, why am I doing an experiment if I can model what's going to happen in these systems? Yet there's still room to be surprised. What can we, how can we take these lessons to larger systems? I think one of the ways we can do that is we can start to enable larger systems that are hard to create otherwise using these dissipation engineering techniques. So one of the protocols we propose, we haven't yet built, has to do with creating the so-called AKLT state on an array of spin-1 systems. And we can use these dissipation systems, things to make the spin-0 and spin-1 manifold the dark state of such a system. And that's starting to get into a quantum system that is complicated and maybe pushing the boundaries of what we can study in the theory land, or certainly that gets theorists quite excited. And so I think extending these ideas to larger systems will get us into the territory where we're able to really push beyond what we can study theoretically. Yes? Yeah. So the question is, for Hermitian degeneracies, we're using conformal field theory to talk about things. What do we need to do, modify in the land of exceptional points? It's a great question. I don't know. Is there an application to prove Riemann's hypothesis here? I don't know. It's a great question.
One more question.
Yes? Yeah, so one example I gave is, a sort of semi-real environment is it happens to be another qubit on your superconducting processor that you have some amount of individual site control over. In that case, you can then use this dephasing trick to turn off the coupling to this sort of accidental environment. But that does involve having actual control to it. But one can imagine a system where it's a two-level system defect in my superconducting processor, and I have a way to actually strongly drive that two-level system. Could be, say, with some electric field and an electrode to that, Could be some other way. If I can find a way to damp out that two-level system, then I can turn off its coupling to my system. People, actually Alp Sipahogel is talking about using his transmons to basically to saturate the two-level systems that are able to couple to his system. So it's kind of a different approach, but there's ways to really to couple to those systems via controlling your qubits. And so that starts to give you ways to drive and to damp out your environment through measurement. So I don't think it's totally impractical.
Great. Let's end the questions there and thank Professor Murch for his outstanding colloquium.
Thank you. Sorry, I didn't get to your question.